Hi everyone and welcome. In this very first lab, we are going to do something simple yet fundamental. When we interact with language models through APIs, we usually only see the prompt we provide and the output that comes back. Everything in between often feels like magic. We have very little to no visibility into what is actually happening under the hood. In this lab, we are going to remove that abstraction layer. Instead of relying on third-party infrastructure, you will run your first language model locally on your own computer. This will allow us to directly observe the internal steps involved in generating text, from raw input to final output. This is why I call this lab Hello Small Language Models. Along this journey, you will be introduced to some of the core concepts and terminology behind language models, including tokenizations, token IDs, tensors, and the fundamental of text generations. More importantly, this lab is designed to help you build the right mental model of how language models actually work. You will begin to see that the output generated by these systems are fundamentally the result of predicting the next words based on statistical patterns learned from data. Meaning that what may appear as reasoning is often the result of a continuing likely sequence of tokens rather than true understanding. With this in mind, let's dive in and run our first small language model locally. Welcome everyone to our first hands-on lab. In this lab, we are going to have a broad overview of a core concept behind the language models. We are going to start with a simple prompt as an input, then we will learn what tokenization really does under the hood, and after that, we will learn about the GPU tensors, and we will see that how language models is conducting its processing to predict the next token one at a time. Then we will learn about the concept behind the decoder, which is a process of converting token IDs to human readable text. And finally, we will see how model is able to generate the output and how we would be able to get a control over the generated text. Apart from this video, I have also created a blog post and GitHub repository related to this lab, in which the link to both of them is provided in the video description below. However, the first step that we need to do, we need to ensure that we have access to the PyTorch and GPU is ready to run. And as we can see here, we have access to the Torch 2.10, which is compatible with CUDA. The CUDA driver is available, and also the GPU, which is Tesla T4, is also available. And we have an access to the 16 gigabyte of VRAM, which is suitable to conduct small processings. We cannot definitely train the model from scratch using this VRAM capacity that we have here. However, for a small example and using fine-tuning using QLoRa would be possible. And I also should mention that I'm using for this lab Google Colab because it comes with the pre-installed environment, so we shouldn't be worried about the local setup. One thing that you need to check here, however, is that you should see that if you're using your GPU instance or no, because it's essential for us. The other thing that we need to do is that we need to install Unsloth. Unsloth is an open source optimizer framework that is helping us to run our language models or all the other deep learning models in a memory efficient way, and they have a broad range of a library that we could easily play around with. And as we are going to use the Google Colab is not by default like have access to the Unsloth, so we need to install them. So we can see that we do the pip install Unsloth, and we need to also install transformer and some other dependency. After having this installed, we need to initialize Unsloth, and with this line from Unsloth import fast language models, we are able to initialize that such that we would have access to the optimizer wrapper, which is responsible to handle the memory in an efficient way once we are using language models. So you would see here, you will see this output will patch Unsloth will patch your computer to enable 2 times faster. The patching here, it sounds a little bit scary. You might think that that impact your operating system, that make kind of change to your computer operating system, but this is not the case. Basically, what is happening, as it is an optimizer toolbox on the slots, it's basically wrapped with the original code, which might be in a Hugging Face, and what it does, it replaces the inefficient part of the code, for example, attention head, with the fast attention. So it makes the code more optimized, the architecture of your neural network more optimized, such that it will run more efficiently in your local computer. So after we finish the job and we close the instance, all of this change would be dynamically disappear, and there would not be any impact on your computer. After having a fast language model in place, we need to load our models. Let me run that because it takes a couple of seconds. So the model that we pick here, it would be LLaMA 3.2, 3 billion parameter instruct version of that, because it is at the end 3 billion parameters that is small enough to run on our GPU, in this case in Google Colab, and at the same time it is capable enough to conduct some of the tasks. So with this, for loading the model, we need to use a fast language model from pre-trained command here. We need to specify the model name as we have been specified here. Maximum sequence length is our context window, the number of tokens that the model is able to process. The bigger it is, it depends to the use case, I would say. It might be more useful because we will provide more context to the model. However, it comes with a kind of price of using more memory. The data type, it controls the computations like mathematical operations, and load in 4 bits. It's essential to be true while you're using Google Colab or your local device, because it controls the memory storage. So therefore, it is important that we would keep that statement to true. And the output, what we would have here, would be the original model, which is pre-trained, and the tokenizer, which I will speak more about that later. Here we have a couple of output that provide kind of information about our model, where it is hosted, which operation system or which framework, Torch framework we are using. Here we can see that we are using the Torch 2.10, which is compatible with the CUDA 12.8. So in overall, what it wants to say that the model is located in our GPU. So therefore, it's important that the data that we are working, it would be located in the same GPU. That's why I also mentioned here that everything need to transfer to a GPU tensor. However, tokenization is a process of turning text into the numbers. The text is understandable for human being. That's how we are communicating with in a writing format to each other, so we can understand that. However, for deep learning, as we are conducting mathematical operation, we need to convert it to the language which is understandable for them, which would be numbers at the end. And how the process of tokenization is working is that we have our input prompt, so explain why a small language model matters, for example. Then we need to convert them into tokens. It can be words, it can be subwords. For simplicity, I only mention here in the format of words. And then they need to convert it somehow using the lookup table that this model has been trained on. So every model, as you can see, every loading of a model is coming with a model and tokenizer tokenizer is a lookup table that has been generated, or dictionary that has been generated during training of llama 3.2 3 billion parameters. So it's important that these model and tokenizer would be matched with each other, otherwise the result would not be appealing. So let's run that. And as I mentioned, as our GPU is located as our model is located in GPU, it is important that token IDs, which would be our data, which we needed to be fed in a model for further processing, is important that it would be also hosted in the same GPU. So as you can see here, we have a prompt explained in one sentence why small language model matters. What we need to do here is that we, as a tokenizer, we need to input the prompt to the tokenizer function, and I specify the return tensor, what should be the format or data format of the token IDs that we would like to generate, which would be the data format of a PT for PyTorch, and the process and everything need to be hosted in GPU, which happened with this simple function of 2 CUDA. So you can see that all these processes that I explained here can be summarized in these single lines. What we would like to do now, we would like to see that what the output would look like here. And as you can see that all these prompt has been mapped to the couple of numbers, which we call it token IDs. And we want to see now backward engineer that to see that what these tokens means at all. As you can see here, we have done this by converting ID to tokens. And as you can see here, there is some reserve terminology that has been mapped with the numbers. So for example, this number is always identified, given this dictionary, the beginning of the sentence or beginning of the text. So it triggered that, yes, new sentence is coming, right? And then you can see that not necessarily every word would be a token. It can be a subword. As you can see, explain is divided into 2 sub words here. We have 849 for X, and then plain would be 21,435. So basically, you could see that there is a subword here, and that's because the way that they are create this dictionary once they were training this tokenizer. So having said that, you could see that all the other words have been treated separately, and there is also reserved token for dot, which is 13 here. But you should also see that we have a special character here, which is identifier for deep learning to show that, well, there is a space in between. So it means that this word here is not part of any kind of sentence or any kind of word here. It's not a subword. It's a separate word from the previous one. So having said that, we are able to generate token IDs from the input prompt, such that we would be able to conduct further processing with that to be able to generate next tokens. So given these token IDs, we feed it to the models. Then the model conducts a probability distribution, and given the probability distribution that we would have here, we would be able to pick the most probable ones, for example. So in this example, for example, we say that explain in one sentence why a small language models matters, and then possibility for that for next token or next word could be because, could be bay, could be day, could be a small, could be innovations. So this is a toy examples. So it is not, from a probabilistic point of view, it's not correct, because some of probability need to be 1. However, I pick it as the example, and most probable one could be, for example, in this case, because. And once we predict one sentence, one word, and then we need to come back and then repeat the process given the additional tokens. What would be the probability? What would be the next tokens? And then next one until we hit to the limit of a number of new tokens. So this code exactly want to say that because we with torch no grad, it means that there is no fine tuning is happening, there is no back propagation, it's only inference. So we said that, well, it's very simple. We just call it model.generate, and then we give it as the input the token IDs of which is derived from a prompt, and then we have max token. This is maximum number of tokens. Then we say do sampling. Do sampling is very important parameters here. If we set it to false, it's we call it greedy. It means that always pick the top token, the most probable one, and do not conduct any kind of distribution or do not conduct any kind of sampling. Yeah. So after that, once we generate that, so this process continue, and then we will have a bunch of words with the length of a maximum new tokens, given the prompt that we have. But we need to convert that to the human readable text, so we need to decode it. So we have a tokenizer.decode. So given the token, we go back to the original words. So let me repeat that. And we repeat it for 3 times. You can also run it for 10 times. It takes maybe a couple of seconds. Yeah, you can see that 3 times we repeat it. As we set this parameter to false, all the output remain the same, and there is no change between them. So if you want to have more diverse output, we need to do sample generation or probabilistic generations simply by changing this parameter to true. Everything remains the same. You just change that parameter to samples. And then let's see how it look like. Again, take a couple of seconds. Yeah, you can see that we try 3 different approach, and we are able to see three different output. So this is pretty much about sampling. However, I would like to give you some kind of more tips about to get more control even on the output of your language models. So we have 3 other parameters. Max new token, as I mentioned, how many tokens we would like to generate after giving a prompt. But temperature, top K and top P, there are 3 additional parameters that you could play with. So sometimes you would like that the model would generate a conservative and repetitive, for example, words, but you would like to also have a kind of, statistic around it. So be innovative, but not too much. Let's put in that word. So with temperature, you would be able to get the control on the scales of distributions. So the low temperature, it means that have a kind of innovation, but be conservative and be careful about that. While I would like to have the model that it generate that think out of the box. So being more creative. In this case, you need to increase the scaling factor, so you would have a more flat distribution probability distribution shape. So therefore, you would be able to generate more creative output. So the first approach is more useful for, I don't know, finance or legal document, and the second one would be useful for creative writing. The other component that we have here would be top K. As you can see, top K would be telling to the model that only pick the top K most probable tokens. So this approach would tell to the model, be creative, but be careful to do not think too much out of the box. No? Top P is acting the same as a top K, but it is more flexible. No, it looks mostly on some of the or cumulative probability across the available words. So it, for example, it look at the portion or percentage of a cumulative probabilities. So it is more, top K is rigid, while top P, I would say that is more flexible. So I would prefer top P over top K, honestly speaking. However, let's run that. We see that here we check on low temperature, and if you read that, you will see that it's more like it tried to guardrail the output. It said that explain in one sentence why a small language model matters. A small language model, you can see that it's repeating the sentence here, like those used in language translation and text generation, can significantly improve accuracy and efficiency. Okay. And then, here would be different, because it said that because they can be fine-tuned for a specific application, making them highly relevant to industries such as healthcare and education. So you can see that by high temperature, the model is not repeating itself, but rather it tried to be more innovative and thinking about fine-tuning, for example, which is true statement. So you can play, obviously, with these parameters and see that to how much you could get conservative or let's say creative. I'll leave it as a kind of exercise to you, and we can also, as I said, play with the top K and top P and the combination between them. So you can see that for this, I would expect that model would be more conservative because we have a sharper temperature or a scale. We have well, not really, because here we have like a higher top P. So and then we have a more, let's say, less top K here. So I expect that this sentence would be more conservative anyway, while this one would be more creative, for example. Again, it depends to your use case, no? So you could play around with that, and you would be able to see different output, and you could decide which parameter works best for your use case. So I also create a couple of exercise for you, so you would be able to play around with that. As I mentioned, the GitHub repo for this code would be available for you, as well as a blog post, so you can play around with this parameter by yourself and enjoy your learning. So in summary, we have been covered several concepts behind language model, in this case small language models, because we could run that locally. We covered concepts like a tokenization, greedy decoding, sample generation, temperature, top K and top P. It has been a lot of information, but you could simply reproduce them. For a next chapter, what I would like to do, we would move toward learning about the chat templates, because honestly speaking, the method that we used here, for example, for prompting, is not a best approach to do in let's say new generation of language models. We really need to follow a kind of fixed structure, which we call a chat template, which I will speak more about that in the next video. By this, thank you very much for your attention, and I'm looking forward to seeing you in the next video. Keep learning and happy learning.